gas, you don't have too much order. In a liquid, you have some order. The intermolecular contacts are getting closer, but in a crystal, they line up like the balls of a pool table. And by studying these, and by virtue of the fact they've got three-dimensional order, means we can start finding out exactly how they're arranged. That's the legacy of Bragg. So taking that as just a simple example, we get the concept of a simple crystal lattice. Lattice doesn't exist, it's a mathematical construction, and then we can see how, if we populate it round, we can see how this identical model, in this case, and there's no particular symmetry driving this is cubane, it's an organic material, you can see how this builds up into three dimensions. And later we see if we shine X-rays on these surfaces, which we find to be crystal planes, we can start to find out exactly where all these atoms are, and more particularly what their structure is. Okay, some pictures. I mean, my favourite is not my pictures. I just got these from the web. But you know, on a morning like this, just think about snow and how wonderfully complicated it is. But as a growing crystallographer, the first thing you see, six-fold symmetry. You see, it's beautiful. Every window, every time it gets cold and you're depressed, go and look at your windows. You see these lovely pictures formed by the instability of crystal growth and the formation of this dendritic structure. And snow is one of those materials with a bit of an identity crisis. It doesn't know whether to grow in this rough form or whether to grow as beautifully faceted crystals. And then sometimes when the driving forces of the weather are a bit high, it renucleates and forms new crystals on. And you get the most gorgeous patterns. So if you think, why can't we predict avalanches? Just look at those pictures. There's a lot of science to be done to do that. This is some of Fiona Meldrum's pictures. She's chemistry here, she's a great one on biomineralization. I stole this one from her. This is calcium carbonate. This is the structure of calcium carbonate we know. We wouldn't know that without the work of Bragg. This is how nature makes calcium carbonate. But we can't do that. This is how we make calcium carbonate in the lab. We're very good at that. That's it. And you find it's a rhombohedral one. You see it's twisted, and the morphology is twisted. Here are the crystal planes. But we don't know how to do this. We can do this. Nature does that effortlessly in every sea animal, urchin. It does it in indescribable ways. If you ever look at the way the hen's egg is built from calcium carbonate, how on earth nature does that ecluse, that's the science that's come up. This is one of mine. This is actually good old humble biodiesel, and these are the crystals that form in it. Beautiful crystals. This is my favourite. I put this on my Twitter page. It's so pretty. And you'll see, look, these lovely spirals. This is what comes out when you cool the fuel, the crystalline components come together, and it forms these enormous plate-like crystals, and they block. This is some of Roger Davies' work from Manchester. This is sodium chloride. This is rock salt. This is on your table, put on your chips. This is what it looks like. It's a horror crystal to grow. My first prof, when I post-up, wanted me to grow sodium chloride. I could have killed him. It was such a difficult material to grow nice, big crystals. There's a whole story. But this is what happens when you start putting a few hydroxide on it. It becomes octahedral in shape. You put a bit of polymer into it, and you can get it to multiply nucleate and form these beautiful cross structures. And this, when it gets cold, why is the Woodhouse laying clear? Because we dump salt on the road with sodium ferrocyanide into it, and it makes the crystal a little bit dendritic. It increases the surface area of the crystal, and it makes the crystal absorb it. All this kind of understanding goes from the great man. This one, okay, so wallpaper for you. This is the work of Sharon Cooper from Durham. These are crystals of glycine, amino acid, now crystallized in emulsions. And look at these structures that colloid science makes of our crystals. Don't need to dwell on this very long. Just don't anyone say that crystals aren't pretty and that they aren't very artistic, and you couldn't have a very nice demonstration of that. Okay. So then so that's the background first. But then crystal chemistry. For a given material, what affects it? Well, we're about molecules. Look, these are all analgesic, aspirin, paracetamol, ibuprofen. We take these when we get an headache. You can see they've all got some similar functionality related there. And for the structure that comes out of these, it's the size and shape of the molecules, the nature of the bonds between them. Thus, and this is the important thing, by making crystals and using X-ray diffraction and Bragg's law to determine the structure and function of the molecule can be related and applied So, speaking as a 60s kid when I wanted to do things that were useful, maybe not so fashionable today, you can use this understanding to design things. Most of our drug development has come from that strategy. So why are they important? Because they're totally ubiquitous. They are the basis of our metallurgy. They are in our food. Why does we break a piece of chocolate? You're breaking the crystal of cocoa butter fat. Yeah. Candles, beautifully crystalline. Endless diffraction patterns of candle wax. Soap and detergent powder. Every time you wash yourself, you're dissolving crystals. Every time you put Persil Automatic in the washing machine, you're dissolving sodium carbonate and sodium sulfate builders that are in the washing powder. All our drugs, when we swallow something, they're crystalline, and all our electronic devices. There would be no chance of an iPhone or an iPad without the crystals that have made that possible. Crystals are also very important in the industry. It's basically how we purify nearly all the chemical materials we make. And making protein crystals, as we'll see later on from the work of Asbury, has been a major driver in understanding the structure of proteins, viruses, and the macromolecules that drive healthcare. So, what is this great man? What did he do? This is diffraction. So as you go through the planes, as you rock through the planes, these beams become coherent when the path length is an integer number, and whoop, you get a nice big peak. What do you get out of that? You get a ruler, you get an atomic ruler. The position of this beak tells you the size of that box we saw earlier on, and then the intensity tells you, or gives you information that tells you where you've got that. Ooh. So X-ray diffraction analysis using Bragg's law gives you the three-dimensional arrangement within the crystal. Just a couple of examples. Well, let's go back to the one I mentioned before. So keeping Britain on the move in winter, as we say, diesel fuel contains paraffins. These crystallize and they make these horrible plates. And these are mostly orthorhombic structure, and these plates reflect the fact that the growth along here is very fast and normal very, very slow indeed, because these long chain molecules sit like this. They block the fuel filters. But if we put inhibitors in them, we can transform, through molecular design, the crystals into not only tiny crystals, but also little equantly shaped. So we stop the crystal growth here, and we leave that one well alone. It's slow enough. And so you get a situation that if you have a pipeline like this, bang, fuel, that's how you can't start your diesel on a Saturday morning like today. And that's because my tank is full of little thin crystal plates of wax. I then put the additives into them, and they flow through nicely. Sounds cheesy, sounds a little bit applied, but without Bragg's discovery, we couldn't have solved the structures of paraffins, we wouldn't know their arrangements, and we wouldn't have been able to design, on a molecular point of view, those additives we put in the fuel. Drugs, so that's fuel. Just want to make sure we're clear that this impacts on our everyday life. This is Viagra, well-known pharmaceutical material, sildenafil citrate. It's a salt with citric acid, and it makes this tablet. The relationship counselor of making that is the crystal. This is what the crystals look like. And in doing that, I have to choose crystals that have the right form to dissolve. It's got to be soluble when you swallow it. And so I have a whole range of materials I have to look at. I might make a salt, I might make a co-crystal, I might make a different form. And to do that, I've got to make sure it's stable, it's soluble, and I can manufacture it. Solid form drugs are entirely developed on the form of the crystal structure. It would be impossible without Bragg's discovery. Totally impossible. We wouldn't have been able to develop the solid forms, we wouldn't be able to make them efficacious, we wouldn't be able to make them safe. Okay, but crystals are actually full of defects, and this, I suppose, was the great discoveries of the 30s through Taylor and later through Charles Frank. And what it is, you get, without going into a whole lecture on defects, that the crystal lattice you've seen sometimes has imperfection. You get an extra row stuck into it, and this we call an edge dislocation, or sometimes you twist it this way, and you can see it creates a little step. And these things become very important. Understanding them, and I'll come into a minute, can come from X-rays. This is just a drug nortriptyline hydrochloride. These are in two structural forms. But things you notice between this are the peaks are in the different positions, so it immediately tells you have a different phase. But the critical thing is, you look at this one, these peaks are all much wider than these. Which means if you put that on a film, the film is blacker because there's more scattering going on because the molecules are a little bit out of position. This is one of my old paraffin structures. This is straight out of a diesel tank. And you can see another thing. You can see that when materials become defected, you get these lumps in the pattern, and sometimes these peaks go downhill rapidly, and there's not much diffraction at big angles. So X-ray diffraction is very good for sorting that kind of information out. So let's have a little look at what's inside the crystal with that basic knowledge. If we were to take a little tiny crystal and we put a saw through the middle of it, like cutting through a tree, you'd see all the tree rings. You'd see very, very similar things in a crystal. You'd see a little bit in the middle where the material nucleated, and then you'd see a whole series of crystal growth sectors developing where the growth took place. And the big faces are those that grow very slowly. The little faces are those that go really fast, and some disappear altogether. And so this is our crystal, this is our cut through it, and then we have a look at all these surfaces. And we can see that if we have these dislocations coming in, that they'll make steps, and the steps will make spirals. And this was Charles Frank's great discovery. And we can see these. These are atomic force microscopes. This is the protein lysozyme, which is beautiful spirals at low driving forces. And then when we go to high driving forces, we get this mechanism. So looking at the surfaces, we can get the mechanisms by which they grow, which as an engineer means I can predict how fast it will grow, which means if I'm designing a process, I can make chemical materials much more efficiently. So let's have some pictures. I'm just going to run you through a gallery of just pictures I've taken over the years. I think a lot of them not published, but I just fished them out of my album. And this is a material called lithium hydroxyl ammonium sulfate. This is a Bragg diffraction image of the crystal. I take the crystal, big crystal, and I scan it across the X-ray beam, and using the so-called technique of X-ray topography, and it just shows lots of pretty things. These are the dislocations, these lovely little lines. This is a dislocation when it moves. This material has a fantastic cleavage plane. So if you squeeze the crystal, you can break it off. Just rather like if you've looked at mica, you can peel the crystals off. And so it's very, very weak in this basal plane. And you see all these lovely dislocations. And these are the growth dislocations that are enabling these faces to grow. A little imperfection here, big bundle of dislocations making the crystal grow fast. Similar here. This is a crystal, same crystal, now at the surface of the crystal. Look at all these, you see all these little etch pits coming through where the crystal after washing has been a bit thinner. These are so-called pendulosum fringes that you get in that. And then here's a bunch in the middle. And these are all the dislocations that come. This is I think I hold the world record for ammonium sulfate pictures. This is ammonium sulfate, which is an agrochemical, an intermediate. Just wanted you to have a look at some of these beautiful dislocations that you get through the material. And these, you can put them in two different Bragg reflections. You can see same crystal, it's disappeared. Oh, where's it gone? Oh, there's one there. Oh, it's disappeared here. So by playing around with the Bragg diffraction conditions, I can characterize the defect fault factors of the material. Look, there's a hole in the material. No, there isn't. It's there. This is a twin. I can image a twin. And these are enormous solvent inclusions. This is the 111 face, and they are very, very unstable. Beautiful. And the interesting thing about materials when they have it that look terrible usually are very interesting inside. This is another one. This is for my thesis. I haven't published this. Typical student. Look at these lovely pictures of the crystal of a garnet. Garnet is a laser material. Look at them here. Bundles, and look at the development of all these sectors, all fighting for the driving force to grow, beating each other up, becoming unstable, trapping in impurities, nucleating bunches of dislocations. And then look at the beauty of, again, this dynamical diffraction you get. This is dislocation, and you can see this lovely black and white contrast, and little tiny impurities trapped in sector boundaries. This is a very ugly crystal. My supervisor told me not to cut it up. Waste of time, he said, taking forever to make a sample of this. I ignored him, typical student. And it had a little treasure trove. I found that it only had one of its morphological forms, and I cut it up, and it had grown very, very fast, and you can see it become unstable. This face did exist. And then it tried to grow fast, and then got trapped with a big lump of solvent and stopped. And the bullies of this face, which is the 110, had squeezed it out. And if you look in the middle of it, it's nearly perfect. It looked appalling. Yeah. Dissolve it up again, he said. Waste of time. So always be curious. This is a bunch of dislocations coming through a sector boundary. Here's the sector boundary. And look, as it comes through, the boundary comes in quickly. It starts to grow fast. There are many. Here I have a whole selection. So I have lots of crystals. Let's have a think as we come towards the end. That I think as we want to see the work of Bragg as an achievement for the university, for Leeds, science, but we want to see it as something going forward. And so as part of the Centenary celebrations, we're marking that with a new professorship. Maybe another New Zealander will come over on the boat. And we're hoping to appoint that later on this year. And we're jointly supporting that with the Royal Academy of Engineering, the new synchrotron diamond light source, if you had a chance to go and have a look at it. Really, really nice. Pioneered by Bragg, the past century of crystallography has yielded enormous advances in the structure analysis of material. And it's led to lots of things that Bragg didn't think about. That's a sign of a really good scientist. They put the seeds out, they don't try and hug it to themselves and say it's mine, the system takes it on and makes it of it. My work on crystal growth could not have happened. Next century challenge will perhaps be to extend and sustain that legacy and start to look at even more complicated materials that are in multi-phase. Nature doesn't work in single phases. The lovely pictures of Fiona Meldrum made by nature, it reflects the fact that that's complicated. It's got proteins to direct how that forms, can change the structure, can change the size, the shape. Real materials are multi-phase, and we don't understand as much about multi-phase material as we could do. Look at membrane proteins as another example. And then multi-scale. How does structure vary across the material? What's the chemical state when it does that? And spatially resolved material. So Bragg's legacy is not just recognised for its past achievement, but I just wanted to say in a series of public lectures, it's part of our future strategy. Okay, so what have I tried to do? I've tried to explain briefly, first on what a crystal is, why they're important, and not only in our everyday life, but also for our industry. Our industry, we all feel needs rebuilding in the spirit of our forefathers. I hope I've tried to indicate the importance of determining molecular structure material, stressing why Bragg's law is so important. I hope I've overviewed how crystals grow and develop, indicate the role that defects are in mediating that process, and illustrating how X-rays can be used to probe perfection and how defects play with that crystal growth process. I think I've tried to show at the end that the university plans to build on that. We're not asleep as a university, we're thinking forward. And then thank you for having me here this morning on this lovely snowy morning, and thank you all for your kind attention.